Section: Introduction. In this section, we discuss the importance of the learning rate as a key hyperparameter in training deep neural networks, particularly for large language models, LLMs. We note that the cosine learning rate scheduler is widely used and effective in various advanced models like Llama 3 and Gopher. However, it has limitations, such as requiring predetermined training steps, which can lead to suboptimal intermediate checkpoints and complicate continual training. To tackle these issues, we introduce the Warm-Up Stable Decay (WSD) learning rate scheduler, which consists of 3 phases. First, a warm-up phase where we gradually increase the learning rate from 0 to its peak. Second, a stable phase where we maintain this peak learning rate for most of the training. And third, a decay phase where we quickly reduce the learning rate back to 0. A significant benefit of the WSD scheduler is that it does not require us to set the number of training steps in advance, making it easier to manage large training runs and allowing for continual learning from stable checkpoints. Additionally, we can adjust the data mixture during the decay phase to include more high-quality data, which has proven effective in recent models. However, we found that while the WSD scheduler can theoretically remain in the stable phase indefinitely, the optimal learning rates vary depending on the number of training tokens. This means that, similar to the cosine scheduler, the WSD scheduler can also produce suboptimal checkpoints if the token count deviates from the initial plan. Moreover, determining the best learning rate remains a challenge, especially for large-scale pre-training, as there is a complex relationship between hyperparameters like learning rate, model size, batch size, and training steps. To address this, researchers have suggested using smaller proxy models for hyperparameter searches to predict optimal settings for larger models. One such method, called mu transfer, facilitates zero-shot transfer of hyperparameters across different model sizes and has been successfully applied to various language models. In our work, we combine the WSD scheduler with mu transfer to explore learning rate transfer between proxy and large models. Our experiments reveal that mu transfer does not enable direct zero-shot transferability of learning rates across different token counts and batch sizes for the WSD optimizer. Instead, we find that the optimal learning rate follows a power law relationship with respect to batch size and the number of tokens. Inspired by this finding, we propose a new learning rate scheduler, Power LR, which is agnostic to batch size and token count, allowing for direct transfer of optimal learning rate scheduling across different conditions. This innovation enables us to conduct expensive pre-training runs without needing to specify the number of training tokens, facilitating early stopping and continual pre-training without compromising convergence. We also discuss maximum update parameterization, MUP, which enhances training stability and the transferability of hyperparameters from smaller proxy models to larger ones. We follow the MUP configuration used in Cerebra's GPT to investigate the transferability of batch size and learning rate across varying training token counts and model sizes. We summarize the changes made to model initialization, learning rate, and multipliers in our study of the WSD scheduler, which divides pre-training into the warm-up, stable training, and decay stages, offering flexibility in managing training steps. Section Summary. In this section, we introduce the Warm-Up Stable Decay (WSD) learning rate scheduler, which improves upon the cosine scheduler by eliminating the need for predefined training steps, thus allowing for more flexible and efficient training of large language models. We also discuss the challenges of optimal learning rate selection and propose the Power LR scheduler, which enables direct transfer of learning rates across different batch sizes and token counts, enhancing the training process without sacrificing convergence. Section: Search optimal learning rate for WSD scheduler with. In this section, we focus on identifying the best learning rate for a small proxy model. We believe that the optimal learning rate remains consistent regardless of model size, batch size, and training steps due to our use of a specific method. To test this, we performed extensive experiments to determine the optimal learning rate for various model sizes and training token amounts. We utilized a specific scheduler with 10% of tokens in the decay phase, following previous studies. All models in this and the next section were trained on the red pajama corpus and evaluated on a separate test set. To explore whether the optimal learning rate can be transferred, we conducted two controlled experiments. In the first experiment, we fixed the batch size at 128 and tested different combinations of learning rates and training tokens. Our findings indicated that the optimal learning rate does not transfer well across a wide range of training tokens, generally decreasing as the number of tokens increases. For instance, the optimal learning rate was 0.0128 for 2 billion tokens and dropped to 0.0008 for 256 billion tokens. In the second experiment, we fixed the number of training tokens at 128 billion and varied the learning rates and batch sizes. We observed that the optimal learning rates did not transfer well across different batch sizes but tended to increase with larger batch sizes. Specifically, the optimal learning rate was 0.0002 for a batch size of 16 and 0.0064 for a batch size of 512. To further understand the relationship between the optimal learning rate, batch size, and training tokens, we examined all possible combinations of these three variables. Our results showed that the optimal learning rate consistently decreases with the number of training tokens across different batch sizes. Additionally, we found that the ratio of the optimal learning rate to batch size remains relatively stable for each training token amount. Based on this, we propose our first hypothesis: the optimal learning rate for the scheduler is proportional to the training batch size. To test this hypothesis, we conducted a thorough hyperparameter search for three model sizes: 12 million, 36 million, and 121 million. After determining the optimal learning rate for each combination of training tokens, batch size, and model size, we focused on the three best batch sizes. The ratios for these batch sizes were plotted, revealing that, for a fixed number of training tokens, the ratio falls within a small range and follows a power law relationship with the number of training tokens. This leads us to our second hypothesis. The ratio of learning rate to batch size has a power law correlation with the number of training tokens, which can be applied across different model sizes. To verify this, we calculated the average ratio for the best batch sizes to estimate the true ratio for each token amount. Our analysis showed that all three model sizes exhibited a similar power law correlation. By aggregating the results, we derived a correlation that allows us to predict the optimal learning rate based on the number of training tokens and batch size. This relationship helps us understand how to set the optimal learning rate before training begins. However, we noticed that this prediction tends to yield a small learning rate for large training datasets. For example, with a 10 trillion token dataset and a batch size of 1024, the predicted optimal learning rate is 0.0011. Considering that our method divides the learning rate by a factor related to the model's dimensions, the actual learning rate becomes very small for larger models. While a smaller learning rate is beneficial for final convergence, it may hinder exploration at the start of training. To address these challenges, we propose a new power learning rate scheduler in the following section. Section Summary. In this section, we investigate the optimal learning rate for a small proxy model using the WSD scheduler, finding that it varies with the number of training tokens and batch size, leading us to propose two hypotheses about its proportionality and power law correlation with these variables. Our results suggest a predictive relationship between the optimal learning rate, batch size, and training tokens, which we aim to address further with a novel power learning rate scheduler. Section: Power Scheduler. In this section, we introduce a new power learning rate inspired by our earlier observations. This learning rate depends on the batch size, the number of tokens already trained, the amplitude of the learning rate, a power law exponent for decay, and an upper limit for the learning rate to prevent excessively large values. Similar to a constant learning rate, our power learning rate does not require us to specify the total number of training steps or tokens in advance, as it only relies on the current number of training tokens. We can also combine this power learning rate with warm-up and decay phases to create the final power scheduler. The power scheduler needs three hyperparameters: the maximum learning rate, the amplitude, and the power law exponent, unlike the cosine and WSD schedulers that only need one. We believe these hyperparameters will work across various model sizes, training token counts, and batch sizes. Since we found that the maximum learning rate has minimal impact on the overall learning rate curve, we set it to a sufficiently high value of 0.02. We then search for the best values of the amplitude and power law exponent. Our findings indicate that the test perplexity is not very sensitive to different values of the amplitude, but it is more affected by the power law exponent, which we found to be optimal between -0.52 and -0.51. This trend holds true across different training token counts, with the optimal exponent consistently falling between -0.49 and -0.53. Based on these observations, we choose an amplitude of 4 and a power law exponent of -0.51 for the remainder of our paper. Next, we compare the power scheduler with the WSD and cosine schedulers in various scenarios. In the first part, we conduct a controlled experiment training 1 billion parameter transformer and mixture of experts models using different learning rate schedulers to demonstrate that the power scheduler performs comparably or better than the others. In the second part, we train a 3 billion parameter transformer language model and a 3 billion Mo language model with high-quality data during the decay phase to compare against strong open-source language models. For all experiments using the power scheduler, we apply the hyperparameters we established earlier. In our controlled experiment with 1 billion parameter models, we train dense and Mo transformer models using WSD, cosine, and power schedulers, all with 1 trillion tokens and a batch size of 1024. We adapt optimal hyperparameters from previous work and evaluate the models on various language tasks, including multiple choice questions. Our results show that the power scheduler consistently delivers better or comparable performance across both language modeling and downstream tasks, even though we only optimized hyperparameters for a smaller dense model. In our realistic experiment, we pre-trained two 3 billion language models, POWERLM3B, a dense model, and POWERMOE3B, a Mo model. We use a two-stage training approach with the power scheduler, where the first stage warms up the learning rate and then applies power decay. POWERLM3B is trained on 1 trillion tokens, while PowerMo3B is trained on 2.5 trillion tokens. The second stage exponentially decays the learning rate to 0. Our training corpus consists of a mix of large-scale, medium-quality datasets. The performance of our models in multi-choice tasks and other evaluations shows that PowerLM3B achieves results comparable to larger state-of-the-art models, while POWERMOE3B, with fewer active parameters, performs similarly to larger dense models.